So I want to talk to you today about carbon-climate feedback, the interaction between climate change and the carbon cycle, natural cycling of carbon, as a primary source of uncertainty in the 21st century climate. So, of course, we have all seen, and has been discussed already this morning, that climate has changed. Climate is changing now. But there's actually much more climate change in the future than in the past in terms of the CO2-driven warming in the 21st century is almost certain to be much greater than the amount of climate change that we have seen so far in the 20th century and up to now. And there are three primary reasons why this is hard to predict. So the three reasons are people, physics, and biogeochemistry, which is one of those big long words with too many syllables, but we could think of that as natural systems. So obviously people are difficult to predict. I've found that all my life, that people sometimes do unexpected things. But in particular for climate change, what we're talking about is predicting the collective socioeconomic development of nations, the political decisions of people, in many cases who have not even been born yet. So it's really a fool's errand to try to nail down what future people are going to do, and that's one of the key levers of uncertainty in future climate. But there's more. Besides the fact that we don't know what people will do, there's the physical aspects of the climate system and how the climate will react to a given amount of greenhouse forcing, a given amount of greenhouse gases. The exchange of energy between the Earth and the rest of the universe responds to that in ways that can be complicated and can involve many interacting feedbacks among different parts of the climate system. But the part that I want to focus on today is the carbon cycle, the biogeochemistry of carbon in the Earth system. And in particular, as climate changes and as the CO2 in the atmosphere changes, there are changes that happen in the land vegetation, for example, photosynthesis and respiration and decomposition, and also in the oceans through the dissolving of CO2 into the ocean water and the changes in the circulations of the oceans. And these changes then feed back and change the climate as well. And as I'll try to argue through this next 40 minutes, each of these three sources of uncertainty contributes ballpark the same amount of uncertainty in the future climate. So understanding what's in store for us and for our children and our grandchildren means trying to understand each of these three aspects of the uncertainty in turn. So I'm going to start with the first one, which everybody can relate to, the uncertainty around future decisions of people with regard to their emissions of CO2. How much carbon will we burn? How much carbon will we choose to burn? And how could we even begin to predict how much carbon people will choose to burn in the future, which turns into CO2? Japanese economist named Kaya developed this simple formula to understand this. It's called the Kaya identity, and there are four terms, and basically it's not rocket science, really just a simple decomposition of CO2 emissions into four factors that when you multiply them together, you get the amount of CO2 emissions. The first one, obviously, is population. That's indicated by P here on the right-hand side. So population times a certain amount of economic activity per person. So think of that as sort of dollars or euros or rupees per person that are generated, times the energy efficiency of the economy. So how much energy does it take to produce 1 unit of economic activity, times the carbon efficiency of energy. So you multiply these terms here on the top together, the population times the GDP per person, times the energy per GDP, times the CO2 per energy, and you see all of the P cancels the P, and the G cancels the G, and the E cancels the E, and you get CO2 equals CO2. So it's an identity, it's quite simple. But each of these four things can change, and of course, some of these things we want we don't want to reduce, right? Strong reductions in population are terrible. That's lots of people dying. Strong reductions in economic activity is crippling the world economy. So we have to target these carbon efficiency of the economy and energy efficiency of the economy and carbon efficiency of the energy. And there are billions and billions of lives at stake, billions of people on our planet. These are two photographs of Shanghai taken 20 years apart. The neighborhood in the foreground is called the Bund on the riverfront. It's about 150 years old. And on the other side of the river, remarkable change in over 20 years in the waterfront in Shanghai as this phenomenal economic development has occurred in many cities in China. There are 7 billion people on Earth, but only 1 billion of us use a lot of energy. 6 billion humans don't use very much energy per person, but 1 billion of us do. The driving force in that four-factor Kaya identity is not population growth anymore. The population growth has actually slowed on the planet. What's really driving CO2 emissions upward is economic growth, economic development. The population of the world is only expected to increase about 30% in this century, but the population of energy users is expected to grow by 300% in this century. A threefold increase in the number of people using a lot of energy. And that is expected to drive huge increases in the amount of CO2 emitted in the world. So economists and demographers can't really predict what future people will do, and instead they rely on scenarios. Try to bracket the possibilities between high emissions and low emissions and in between emissions. So what we see here in the top plot is time from 1850 to 2100. In the black line there are the historic CO2 emissions in petagrams of carbon per year, same thing as gigatons of carbon per year. And then each of the colored lines that follow on from the present are scenarios out to the end of the century of emissions. And you see a blue scenario that drops off very quickly from about now, quickly reducing CO2 emissions across the world, falling to zero or near zero by the end of the century. And on the other hand, in the dark red line, emissions which don't peak until 2150, well into the next century. And then a couple of scenarios in between. And the total amount of carbon that's released over the entire period between 1850 and 2100 are indicated by these big bars at the bottom. They're called representative concentration pathways in the ICCC report. So peaking emissions in 2020 all the way out to peaking emissions in 2150. These are not predictions of future behavior by people. They're really what-if experiments. What if we emit this much? What if we do that? What if we do somewhere in between? And then climate models are used to explore the consequences of people making those possible decisions, those future decisions. And of course, it depends on economics, and it depends on politics, and it depends on stuff that we can't predict. That's why we do the scenarios instead. I'm having some problem with that slide. Maybe I can't use that slide. There are big choices ahead. The past CO2 emissions have led to the amount of warming that's indicated by this black line. So since 1900, we've had roughly 1 degree Celsius of warming around the world. And it's caused some disruption. We just heard this morning about droughts and about floods, about intense storms, about all kinds of significant impacts that we've had already. But you haven't seen anything yet compared to what's in store if we choose these higher scenarios. I've shown here in the orange line on the top and the blue line towards the bottom the future warming that's expected if our descendants collectively across the world choose to go for that high emissions scenario, leading to something like 5 degrees Celsius of warming above pre-industrial by the end of the century, versus the low emissions scenario, the peaking emissions in 2020 and rapid decarbonization of the world economy in the blue, leading to about 1.5 degrees Celsius of warming above the pre-industrial level. And you see that the difference between these two pathways is about 3 degrees Celsius of global warming. So the primary source of uncertainty in our future is what our descendants choose to do. What do they choose to do about our problem, about our world? The next piece of uncertainty, the next piece of decision point, if you will, is once our descendants decide how much carbon they're going to put into the atmosphere, what is the effect of that extra carbon on the climate system? And that's essentially up to physics. So the photons come in from the sun and the energy is re-emitted by the solid Earth, gets captured by greenhouse gas molecules in the atmosphere and re-radiated back downward and so forth, and warms the planet. But those effects of the extra radiation on the hydrologic cycle, on crop productivity, on floods and droughts, on intense storms and sea level rise and so forth, involve some rather complicated interactions between the radiation and the other parts of the Earth system, which is the province of all of climate science to answer. It's certainly not my own. There's a community of thousands of people in many, many different countries, certainly here in Sri Lanka as well, that work on the physical aspects of the climate system. And some of these feedback mechanisms are quite important. So we have the sun beating down on the Earth, and the amount of energy from the sun has to be balanced by energy that goes back out to space. We can see the energy coming in, of course, it's sunlight, it's visible radiation. The energy going back out is in the infrared part of the spectrum. It's not photons or wavelengths that our eyes can see, but certainly extremely important, carries all of the same amount of heat back out to space that comes in from the sun. This is a little formula that shows that sunshine times the part that doesn't reflect off, so 1 minus the albedo is the fraction of sunlight that remains on the planet. The Earth absorbs sunlight as a disk, so it casts a cylindrical shadow out into space. So the sunshine is absorbed only on the daytime side, obviously, but the emission of energy to space is proportional to the fourth power of temperature there on the right-hand side. We say sigma t to the fourth. But the Earth emits energy as a sphere. So it absorbs as a disk, emits as a sphere. The sphere has an area that's bigger than the disk. The sphere has 4 pi r square meters of emission. So the pi r squareds cancel, and we're left with a temperature of the Earth that's minus 18 degrees Celsius, so very, very cold. If the surface of the Earth was minus 18 degrees Celsius, the oceans would be frozen to the bottom. The world would be a snowball in space, floating around, uninhabitable ice world, orbiting here instead of us. So we owe our very existence to the greenhouse effect, which re-radiates some of this energy back down and gives us an observed surface temperature of about 15 Celsius, 33 Celsius warmer than it would be without the greenhouse effect. Thank goodness for the greenhouse effect. So we can take this rather simple energy balance model that we just looked at and consider 240 watts per square meter of available energy coming in. That's our solar forcing. The climate system then does something. You can imagine it as a big black box, a machine that takes that 240 watts per square meter and converts it to a surface temperature of 15 C. Think of it as a system which absorbs sunshine into climate, into surface temperature. And what I want to ask then is, how sensitive is this system to a change? So on top of our 240 watts per square meter, what if I add 1 more watt? What if I either turned up the sun by a watt or increased the greenhouse effect by 1 watt per square meter? What would be the effect then on the other side on the surface temperature? And on the left-hand side, we call that climate forcing. On the right-hand side, we call it climate response. And the sensitivity of the climate system is just the ratio of the response per unit forcing. So how many degrees per watt? If I add 4 watts per square meter from doubling CO2, how many degrees of warming do I get? So answering that question from first principles is very difficult, and that's why climate science has been working on this for 150 years. The little black box question is up in the upper left-hand side, but you can imagine I put my delta forcing, my little 1 extra watt per square meter in, and it produces a little change in the surface temperature. But that's not the end of the story. Because if we warm the Earth a little bit, we get some amplifying feedbacks. For example, adding to the surface temperature will evaporate more water from the oceans. Water vapor is an even more powerful greenhouse gas than CO2. The extra water vapor traps more outgoing long-wave radiation, re-radiates it down to the Earth, adds more to the surface temperature. And changing the temperature a little bit melts some ice and snow, and that allows more sunshine to get absorbed, and that increases the temperature even more. So this is another little amplifier. Some of the extra water vapor will turn into high, thin clouds way up in the sky at 7 or 8 or 9 kilometers up, and those clouds trap outgoing radiation as well, add to the surface temperature. So all of these things will tend to amplify the initial effect of the CO2. But there are also negative feedbacks that damp the effects of the CO2. So for example, as we make the surface warmer, we mix the atmosphere more because the hot air rises and it carries the heat up into the atmosphere where it can be released to space, and that will actually tend to cool the climate because it gets the heat up above all the CO2 and water vapor so it can radiate back out to space. So this acts almost like a thermostat that reduces the amount of warming. Some of the extra water vapor we put in the sky turns into low clouds, which shade us from the sun and prevent the sun from reaching the surface of the Earth, reflect it back to space very efficiently. So that can be a negative feedback. All of these feedbacks act together. We can look at the total sensitivity of the climate system by looking at past climates, but projecting into the future is very difficult, quite complicated because of all these difficult interactive physical properties. There are many different methods for evaluating the overall climate sensitivity, and this is from a famous paper about 12 years ago that considered dozens of different studies, reviewed dozens of different studies of climate sensitivity. So for example, we can use the instrumental record looking at climate change in the recent past in the upper left. We can look at climate models in the lower left. We can use volcanic eruptions and look at the degrees of cooling per watt of forcing from that. We can look at millions of years of climate change in the deep past, looking at paleo data. And each of these gives us a little sort of probability bell curve for how sensitive the Earth's climate system is. What we tend to find is that taking all of these pieces of evidence together, the overall sensitivity of the system is between 2 degrees and 4.5 degrees Celsius of warming per doubling of CO2. So remember, uncertain people give us about 3 degrees of uncertainty in future climate, and this is uncertain physics. Uncertain physics gives us about 2.5 degrees of wiggle room about uncertain climate in the future. So finally, I'd like to now draw your attention to the natural cycling of carbon in the system, and I'm going to argue that this is giving us a similar degree of uncertainty in future climate as the people and the physics. The global carbon cycle consists of 3 main reservoirs that exchange a lot of carbon among them. The atmosphere is the one we've been talking about in here. The atmosphere has about 800 gigatons or petagrams of carbon. Each of these pools have a number in them. That's how much carbon is in that reservoir. The carbon in the atmosphere is almost entirely CO2, 800 gigaton. What's a gigaton? A gigaton, if you had a box that was 1 kilometer wide by 1 kilometer long by 1 kilometer tall, and you filled that box with water, 1 cubic kilometer of water, that weighs precisely 1 billion tons, 1 gigaton. And so there's 800 times that much carbon in the atmosphere as CO2. The land, the biosphere on land, the plants, the soils, the microbes, together, more than twice as much carbon as the atmosphere, so about 2,000 gigatons on the land. But the ocean is the big one. The ocean contains, in dissolved form, about 38,000 gigatons of carbon, mostly as bicarbonate ion, which is also related to the formation of seashells and corals and things like that. Humans dig up about 10 gigatons carbon per year as coal, oil, and gas, set it on fire to drive the world economy, and release about 10 gigatons to the atmosphere. But notice that the atmosphere is only increasing by about 5 gigatons per year. So half of the carbon that's transferred by us, by our global economy, out of the ground and put into the air, half of it lands in the air and the other half goes away. It's a wonderful thing that half of it goes away, because it means the rise in CO2 is only half as fast as it would otherwise be if it wasn't going away. But where has it gone? The only other 2 places that it could go are the oceans or the land, but it's very difficult to find the missing 5 gigatons because the atmosphere annually sucks down 120 gigatons as photosynthesis. So think about that just for a moment. The atmosphere contains 800 gigatons of carbon. Plants turn 120 gigatons of that 800 gigatons into plants every year through photosynthesis. Left to their own devices, plants would eliminate every molecule of CO2 in the atmosphere in 7 years. There's only 7 times as much CO2 in the atmosphere as 1 year of photosynthesis. But of course, we're not running out of CO2. How is that balanced? Of course, the rate of growth of plants is pretty much balanced with the rate of death of plants. So life and death have long been in essential balance here. 120 gigatons, give or take, of decomposition and death balances 120 gigatons, give or take, of growth. And similarly, the oceans dissolve about 90 gigatons a year, mostly in the cold water, because cold water can hold a lot more CO2. As anybody who's ever left a soda or a beer out on the table, you see what happens if you let it warm up, the CO2 comes out of it. Similarly with the oceans, the cold water dissolves the CO2, it's transported into the tropics, the CO2 then degasses back into the atmosphere, and this 90 gigaton round trip into the ocean and the 120 gigaton round trip into the land dwarf the 5 gigatons that we're looking for. The missing carbon that's not coming into the atmosphere is difficult to find. It's a needle in a haystack. We're trying to find a small residual in very, very large exchanges that occur in the natural world. Rather complicated graph, sorry about that. On the top shows fossil fuel emissions over all the years since 1750, and in the bottom, the emissions are shown in the upward part of that graph, and then each of the places that it goes are in the bottom part of the graph. The light blue is the atmosphere, which I just showed you. The oceans also take up a lot of carbon on the net, and that's actually been worked out by oceanographers over a period of years. Back in 1964, the US and the Soviet Union agreed collectively to stop blowing up nuclear weapons in the atmosphere. Good for them. So what do you think they did right before the treaty went into effect and they had to stop? They blew up a lot of nuclear weapons in the atmosphere in 1964, and this created a large slug of radiocarbon, of carbon-14, and it chemically, biologically behaves the same as any other carbon, but it's got a little sticker on its forehead that says, I was made in 1964. So the oceanographers went and found this bomb radiocarbon in the oceans and were able to deduce the rate of transfer of anthropogenic CO2 into the oceans. As a residual, then, I'm showing in the green there the amount of uptake on the land. So about half of the missing carbon has gone to land and half to the oceans. But the future of these uptake processes into the ocean and into the land is much harder to predict than the temperature. The temperature is actually an easier prediction than the future of photosynthesis and respiration and ocean circulation and ocean chemistry and so forth. So where has all the carbon gone? How did it get there? And when will it come back to bite us? Into the oceans, there are 2 major processes that take CO2 into the oceans. The first is simply solubility. If you had a beaker of water and there was a certain headspace above that water and you pump CO2 into the headspace, then there's more CO2 gas in the air than there is dissolved in the water, and so the concentration gradient is down and some of the gas will dissolve into the water. The same chemistry that makes bubbly water, makes Pellegrino or Perrier water, also acidifies the ocean and makes dissolved CO2 in the oceans. It actually turns out that the solubility pump that removes CO2 is limited not by the chemistry, but by the physical mixing of the ocean. The warm water floats on the top, and that exchanges CO2 very well with the atmosphere. The cold water, which can hold much more CO2, is heavy and dense, and it lays at the bottom of the ocean and doesn't physically touch the atmosphere, so it's very difficult to get the CO2 in there. The biology in the ocean also delivers CO2 to great depth through phytoplankton, photosynthesis at the surface. They get eaten by zooplankton, they get eaten by fishes, and so forth. When you get a big enough particle, they can sink down out of the light, be decomposed at depth, and deliver some carbon to the deep ocean. That's called the biological pump. It's like a slow, steady rain of organic debris down from the surface of the ocean into Davy Jones' locker. On the land, let me first say that everybody knows that photosynthesis removes CO2 from the atmosphere. This is why we were given trees to plant, right? Because the trees will take CO2 out of the atmosphere. But it's easy to forget that this is only a temporary excursion from the atmosphere into the plants, because like us, plants get old and eventually they die. And when they die, they're decomposed by microbes, and the carbon goes back into the atmosphere. So when we say that roughly half of the missing carbon has gone into the land over a period of 55 years since we've been making good measurements, what I'm saying, and I want to say this slowly and carefully so everybody's sure they understand it, what we're saying is not just that plants photosynthesize, we're saying that as a whole planet, things are growing faster than they're dying. There's actually more growth of plants each year than there is death of plants. And this has been sustained for 55 years since measurements started being made at the end of the 1950s. We know that there's been an accumulation of carbon in the biomass of the planet, really remarkable. When this was first discovered by oceanographers looking at the bomb C14 and atmospheric scientists looking at the carbon dioxide in the atmosphere, they published papers in the 1970s explaining that things are growing faster than they're dying, and ecologists thought they were crazy. Ecologists said, are you nuts? Not only are things not growing faster than they're dying, we know they're dying faster than they're growing. Haven't you heard the famous song about paving paradise and putting up a parking lot? People are destroying the rainforest, they're digging up the prairie, they're building parking lots and shopping malls all over the world and destroying biomass at a phenomenal rate, which is true. Nevertheless, on the planetary scale, things are in fact growing faster than they're dying. So this is a remarkable mystery, and it's an incredible service that the ecosystems of the world provide to us, the human race, by effectively reducing our fossil fuel emissions 25% for free. How does that work? How can we make it work faster? Is that carbon still going to stay there for another 30 or 40 or 100 years? Or is it going to start coming back out? Or things going to start dying faster than they're growing? That's the key of the terrestrial carbon feedback. Part of the process that sequesters carbon, why are things growing faster than they're dying? Part of that is the CO2 itself. Down at the level of a leaf or a chloroplast, certainly if you give extra CO2 to a plant, it will grow faster. If we took one of these lovely pomegranate plants and put it in a greenhouse in doubled CO2, it would grow faster than one was put in normal CO2. But out in the world, typically plants need some other stuff besides CO2. They're not CO2 limited. For example, plants need nitrogen, plants need water, plants need light, plants need room to grow, plants need freedom from pests and from guys with chainsaws. Plants need all sorts of things besides CO2, and it's very problematic to imagine that just adding CO2 to the atmosphere will cause an unlimited amount of plant growth because of these other limiting nutrients. However, we're taking care of some of that for plants as well. For example, we are fertilizing like crazy across the planet, both intentionally for agriculture and unintentionally through air pollution. When we make cars and industry, some of the combustion that happens in industrial combustion actually burns some of the air. We take some of the nitrogen from the air and react it with the oxygen from the air to make nitrogen oxides, which then oxidize again to nitrate in the clouds and come down as rain. It's like, free fertilizer from the rainfall that fertilizes plants. And between the CO2 and the nitrogen, we're growing a lot of plants around the world. Land use change certainly destroys biomass and turns it into CO2 through deforestation, but some land use change can also wind up accumulating carbon. So for example, in the Western Hemisphere, my ancestors arrived hundreds of years ago from Europe, and they cut down a lot of trees and they built a lot of farms, and all of that carbon that was in the primeval forests of North America was turned into CO2. But in the last 100 years, the family farm in the United States has essentially become untenable. And now agriculture has moved into large businesses. The people who used to be farmers in New England moved into towns and got jobs in offices and so forth, and those trees have been growing back, not just in the eastern United States, but also in Western Europe and in parts of Asia. And all of those trees in those reforesting areas used to be CO2 molecules, so that's sequestering some carbon. And then finally, the response to changing climate itself has caused some carbon sequestration. As the Arctic has warmed, the sea ice has melted, but besides that, the growing season is much longer in the boreal zone than it was, say, 30, 40 years ago, almost twice as many frost-free days, and so you have shrubs moving into places that used to be tundra, and all of those woody plants replacing herbaceous plants have sequestered carbon as well. So all of these things have removed a lot of carbon from the atmosphere, sequestered it both in the oceans and the land. The trouble is that the CO2 fertilization is a gift that keeps on giving. If we increase the CO2 a lot, and CO2 fertilization is very effective, great, because it's going to continue vacuuming up CO2 from the atmosphere. But if these other mechanisms dominate, so for example, nitrogen fertilization, you can put some fertilizer on your crops and they'll grow faster, but putting 10 times more fertilizer will not make them grow 10 times faster. In fact, it'll probably kill them. So more nitrogen fertilization, once you've met nitrogen demand, is a losing game. You wind up saturating that sink. And similarly with land use change, you grow forests where there used to be farms. Once they've grown back, then things are dying as fast as they're growing again. You no longer have a sink. And especially the warming in the boreal zone is a gift that stops giving, because a little bit of warming will grow trees where the tundra used to be, but a lot of warming will thaw the permafrost and then decompose all that organic matter and pour tons and tons more CO2 into the air. So many of these land sinks are very, very vulnerable. And carbon climate feedback is about the changes in those sinks over time. I have too many slides, so I'm going to skip some slides. Pardon me. Sorry about that. Let me say a little bit about the oceans. The vertical structure of the ocean is kind of interesting. The North Pole is on the right, the South Pole is on the left, the equator in the middle of the diagram. The at the equator, the surface water is very warm, colored red, and it's buoyant, floats like a raft on top of the rest of the ocean. 95% of the ocean is below that. It's extremely cold, averages about 3 degrees Celsius, and much heavier than the surface water. So when we exchange CO2 between the atmosphere and the ocean, we're really only exchanging it with that surface water. And the only way to get the CO2 into the deep water, which is where the CO2 has to go in the long run, is at the poles in the winter. So right this time of year, up around Greenland, the water is very cold, takes up a lot of CO2, becomes heavy, and sinks. About 1/1000th of the ocean mass sinks at the poles each year, carrying our CO2 with it. So it takes 1,000 years to turn that entire ocean over and exchange chemistry between the ocean and the atmosphere. Very, very slow process. We've measured this all over the oceans with ships, with sampling, and besides sequestering CO2, it actually also changes the chemistry of the oceans, causes ocean acidification, which is deadly for coral reefs and for all organisms that build shells out of calcium carbonate, out of limestone. So this is, it's a good way to get rid of CO2 from the atmosphere, but it's a terrible thing to do to the oceans in terms of the ocean food chain, in terms of the ultimate survival of marine life. On the land, we've discussed CO2 fertilization, and I'm going to skip some of my slides because, as I said, I put too many in this presentation. I apologize for going through this so quickly, but I want to say that besides climate models that are driven by CO2, there's a new class of Earth system models that are used for the climate change assessments, which instead of prescribing the CO2, we prescribe CO2 emissions according to these scenarios. So if China and India and Africa wind up building industrial economies with coal, that leads us on a very high emission scenario. If they wind up using primarily renewables, it takes us on a lower scenario. But for the same scenario, then different models predict a different amount of land uptake and a different amount of ocean uptake. So this is a comparison of about a dozen different Earth system models. You can see that all of them take up carbon in the ocean and they take up carbon in the land. And starting about now, in the 21st century, the ocean models spread out. So by the end of the century, some ocean models take up as much as 9 or 10 gigatons of carbon per year, as much as the entire current fossil fuel emissions, remarkable. And other ones only take up about 4 gigatons per year. But on land, it's much worse. On land, some of the models take up as high as 10 gigatons carbon per year by the end of the century. But in other models, something terrible happens in the middle of the 21st century, and you can see some of those lines turning down and actually releasing carbon. That's because as climate changes, the tropical forests dry out because the air is much warmer, can evaporate more water. The trees die in those models, and the trees then decompose, and the carbon is released to the atmosphere, adding tremendously to the amount of CO2 in the atmosphere, giving us a spread of over 300 parts per million of CO2 in the atmosphere by the end of the century for the same human emissions. So the same fossil fuel emissions produces an uncertainty of about 300 ppm in CO2, simply because the biology of the world interacts with the climate system. It's not independent. This has actually gotten worse. In the most recent IPCC assessment, about 350 ppm spread in the CO2, leading to about 1.5 degrees Celsius of spread in future warming for the same physics and the same emissions. So it's about half the uncertainty that arose from different human choices, and about 2/3 of the uncertainty that is due to changes in the physics, the uncertain physics. This is a huge, huge spread. One of the best sources of data that we have to be able to distinguish among these different process models and better understand future interactions between biology and CO2 and climate is a new set of satellite missions which began in 2014 and are leading now to new insights into the carbon cycle by measuring CO2 everywhere from space, about 1 million measurements a day collected from an orbiting platform launched by the United States. There's also a Japanese satellite, and European satellite is coming soon. This is a map, a moving map of CO2 in the atmosphere as simulated by a model that's developed in my research group. And the model predicts the biology and the exchanges with the ocean. And you can see the diurnal cycle, the day, the sun going up and down, moving from east to west, and then these swirls of low CO2 developing over the northern hemisphere because of growing plants in the summertime. As these different levels of CO2 get blown out across the atmosphere by the winds, they spread these concentration gradients around. The satellite can then be used to observe these patterns and allow us to detect problems with the models, mistakes that the models make, improve our prediction, our ability to better understand the interaction among the natural cycling of carbon and the fossil fuel emissions and the climate system itself. So to summarize my remarks, the 21st century climate is uncertain because it's hard to predict three things. The role of people and policy, decisions of people we don't know and haven't even been born yet. Secondly, the clouds and radiation, which is the physics. And thirdly, the behavior of carbon in lands and oceans as it reacts to the climate system itself. People will remain unpredictable. I make this strong forecast that as people have been unpredictable in the past, they will continue to be unpredictable in the future. It's unlikely we're going to discover the governing laws of human behavior. So I think we're probably going to be unable to nail down that first source of uncertainty. There's been fantastic progress over the last 20 years on understanding the physical feedbacks in the carbon cycle, and those models have improved a lot. The uncertainty has come down. One of the most key elements for future uncertainty reduction is therefore the carbon climate feedback, deserving high priority so that we can as we better understand the carbon cycle, we will better be able to predict what's coming in the future for us. And the new observations of CO2 from space will hopefully dramatically improve our understanding of these systems. Thank you so much.